So this video is video number 2 on the shortest possible route, okay, in networking. And there are many algorithms out there as well, but one famous one is Dijkastra, the algorithm. So this one is a special type of algorithm, and we will explain how it actually goes. But the first thing is, let us establish a network diagram first. So suppose you have these nodes connected like that. Okay, so this is our network diagram, and then suppose we have been asked find the shortest possible route. So maybe they might tell you, okay, use the Dijkastra's algorithm or maybe any other, but this video mainly is focusing on the Dijkastra's algorithm. So how do you find that? What I can advise you is, first you need to make a table there, list all the points in the network. It's running up to 5, if you will notice, and then from there, what you would do is, looking at your diagram, you want to start making the possible routes. Like, you're starting from 1, you have to find the starting point, which is 1 there. So you ask yourself, from 1 to 1, it's just 0. You don't need to make any movements to go to 1. That's why that one always be 0. So you even put here the marking of the routes. The routes always sit in this vertical axis. So from 1 to 1, it's 0. And then at the initial starting point, it's assumed that 1 to every other node initially is infinity. That's the assumption that is taken in Dijkastra's algorithm. So you first begin with the original starting point and ask yourself, from this original starting point, of course the movement will just be 0 because you don't need to move to go to that place. Yeah. So after that, then you now start considering, okay, having discovered having established your starting point now, how do you move? What are the possible places that you can visit or move from A? You'll notice from the diagram that from A you can actually go to 2 and to 3. Currently, those are the only 2 places that A is currently connected to directly. So 2 and 3. So between those two, you ask yourself which one has got the shorter distance or the shorter weight or a smaller weight. It's actually 30, which is 1 to 3. So you will be updating your table below. So 1 to 2 initially it's not going to go there yet. Oh, sorry, it's going to go there, but there is an amount of what, 100. You, in fact, you record what you're able to see, you can record. So it has shown you that it's no longer infinity, because infinity was just an assumption from the onset, but now you've gotten the accurate values from the movements that we're seeing in the diagram. So now what about 1 to 3? 1 to 3 from our diagram, it's 30. How about 1 to 4? Well, as at now, 1 is not directly connected to 4. Hence, you will maintain the same infinity sign until you have a direct link to 4 somehow. That's when you come and put a figure. Even 1 is also not directly connected to 5. You maintain the same infinity. Hence, you're just left with about 2 figures. You will not consider 1 to 1 because we are already from there. You get, you already considered 1 to 1 is 0. That's why, if anything, once a point is considered, we even do this. Show that do not take anything there again. Yeah, it's already visited, in other words. So you have 2 points, 130. What are you going to do next? The way the Dijkstra's algorithm works, looking at this table, you look at this same second row that you're just from making, and then pick out the smallest of these 2 answers, which is the 30. And this 30 will guide you that from this 30 came from which connection? It was 1 to 3, meaning the next route you've reached that is at 3. That's how you move using the Dijkstra's algorithm. So having reached 30, which is having reached point node 3, there now, where are you going to go to next? So if you look at the diagram, 3 is connected to 2, to 4, and to 5. It's connected to about 3 places which it can go to. So as long as the town is not visited, what do we mean by not visited? It has not yet been marked in this vertical line where we're now putting the routes, like 1 to what, so far. So that's why I would say it's not visited. So as long as we do not bring the number into this vertical line or along the y-axis, if you want to use the graphical language, then you know that that place is not yet visited. So there's still 2 a possible place to go to. There's a 4 and 5. So looking at point 3, assume from point 3 to 2, what's the figure? I know people would say 20, but is that really the answer? No. For you to have reached 3, you've already encountered the weight of what? Of 30. So it will be 30 plus any other thing. That's how it will be. So 30 plus 20 will give you 50. So you can record your 50. But I beg your pardon. In fact, the arrows were supposed to be like this. Yeah. Sorry. So the arrows was supposed to be also shown. So 3 to 2 is not even a root. I beg your pardon on that one, because you can't go opposite the arrow, if you get what I mean. So the only places that 3 can go to is 4 and 5. Yeah, let me make that correction. 3 can only go to 4 and 5 only. Those are the only direct connections that are there for 3. So you will notice that from 3, as we said, you already counted 30. So 30 plus 10 to go to 4, it will be 40. You can record the 40. So at least you put your 40 there. It's now a known distance. And then 3 to 5, you already have a 30 plus 65, 95. You put your 95 here. So 3 to 3, in fact, this point once you just box a figure, you're not taking anything there, so that root is being gone. Then what about these roots like to 2? Okay, since 3 can't go to 2, you just repeat what 2 has exactly. It just comes back the way it is, because you can't go to 2 directly from 3. That's what it's just telling you. So you just do that and bring down your 100 the way it is. No changes have been made in short to point 2. You have not found any shorter distance to 2 yet, apart from the 100 that was depicted earlier on. Next, what are we going to select? We are done with the third row, right? We have examined all the rows that 3 can go to, and after you're done with the row, you always do this. Amongst the new figures in the third row, which one is the smallest? 40. You box it. And 40 is under which column? 4. And 4 becomes a new connection in the network. So already the way these are being aligned, they are actually showing you where the shortest possible route to be passing. That's the nice part about Dijkastra's algorithm. As you're making these points, it's marking for you the route. Then you're moving. So you're at point 4. 4 can't go back to 2 because of the arrow. So 4 can only go forward, which is to 5 directly. And that route is adding up to 50. Okay. So 4 to 5 is 50, but we said you can't just say 50, because for you to have reached 4, you had encountered already some weights along the route. So that was a 30 plus a 10, that's 40. 40 plus 50, 90. So it's showing us that at 5, we should actually record 90. What was under 5 initially? That was 95. Huh? So you notice that 90 is actually smaller than 95. So it's the best figure to actually assign at 0.5, because 90 is smaller. When you're looking at shortest possible route, you should always assign the smaller number, even though there was a previous number recorded earlier on from a previous trial. That's how it is. So we put a 90 there and record. And what about these other nodes or other connections? So yeah, so there will be no 4 to 4 already boxed it. As we said, once you just box a state number, then you're done. Basically, you've handled it. And then I think that's it for the rest. Wow, 2 obviously remain the way it is. This one has gone. Yeah, so you just have 90 and 100, and of course 90 will be a smaller one, and that's been the last node in the network, and we'll end here. So this already has actually shown us that the shortest possible route, just follow the boxes, the lines where the boxes are. It will be showing us, okay, this is where the route is. So this is showing at 90 is under 5. The other route will be 4. From 4 is also 3. From 3 back to 1, which was the starting point. That's how it is. As long as something was boxed, that's the route you're following. So basically showing that it's 1 to 3 to 4 to 5. And even when you use what they call trial and error is where you just start counting the possible totals you can get from each route. You can maybe start counting, okay, what do I get from 1 to 2 to 4 to 5? You add. What do I get from 1 to 3 to 4 to 5? You add. You will still find that you're proving with the answer that Dijkastra is giving you, whether someone uses trial and error or uses the standard methods that are depicted, you find that these are the same. So therefore, even mark to your maybe your lecturer just to see that okay, this is the root and that is our shortest path in the network using Dijkastra's algorithm.